In today's session, I'm going to talk about a topic that troubles most of the students. Even if we keep all the practical effects aside, like the least count of the instrument, like the scope of human error. So let's try to understand. This is all mathematics, but let's try to understand. So if this is a metal rod, are you expecting any current to enter into this rod right now? Hello, dear students. In today's session, I'm going to talk about a topic that troubles most of the students. Your current electricity chapter may be very good, but I'm very sure that there is one topic in current electricity where you struggle, and that topic is potentiometer. So let's understand this topic and ensure that you are never troubled in this topic ever again. Let's begin. So what exactly is a potentiometer? All right, obviously the question begins from here only, that what exactly is a potentiometer? So I will say that potentiometer, okay, potentiometer is a setup. Okay, now please pay attention. I'm not using the word device. It is not a device. It is not something which is ready-made. It is something that we prepare. Now, of course, we do get ready-made potentiometers also in market these days. But uh, what we have to understand is that it's a setup. Okay, it's a setup to measure potential difference between 2 points. Okay, it's a setup to measure potential difference between 2 points without error. Okay, now what does that mean? Like, without error, we have to understand this statement properly. Okay, so we know that in experimental work there is always a scope of human error. Okay, so I'm assuming that the experiment is being performed by God. In other words, error can't be there, human error can't be there. The person who is doing the experiment or who is doing the measurement, that person is a perfect experimental physicist, and he doesn't commit any error, so there is no scope of human error. Then there are other kind of error that get incorporated because of the least count of the instrument. We are not talking about those errors also. Now what are these errors that we are talking about? Like, what is the error that I'm trying to eliminate? So guys, when we use voltmeter to measure potential difference between 2 points, that is the instrument that we say is designed to measure potential difference between 2 points. When we use that, even the theory suggests that there will be an error in the measurement. Like, even if we keep all the practical effects aside, like the least count of the instrument, like the scope of human error, okay, even if we say that all these things are totally absent, even then a voltmeter will cause some error in the measurement. And this is like, we are saying this on the basis of theory itself. Like, I'm not taking into the practical effects into account. All right, so I think it is imperative that we first understand that what is wrong with the voltmeter. I'll spend some I'll spend some time on this, and then we'll start with understanding the potentiometer. So potentiometer is a setup that is used to measure potential difference between 2 points without error or accurately. So basically, there is something that voltmeter does incorrectly, and potentiometer gets rid of that thing. So let's understand what is that thing. So we are now focusing on that what's wrong with a voltmeter. Okay, let's try to understand this. So to understand this, let me draw a circuit. Okay, this is a very simple circuit in which there is a battery, let's say 1 volt. There is an internal resistance of the battery, let's say 1 ohm. Okay, and there is a resistance which is like, let's say 999 ohm. Okay, let's call this resistance as R. Okay, in this circuit, if I ask you that how much current is flowing, you will calculate it to 1 volt divided by the total resistance, which is 1000 ohm, and you will tell me that 1 milliampere current is flowing in this circuit. And then if I ask you to calculate the potential difference, to calculate the potential difference across the resistor, you will use I into R. That means you will say 1 milliampere multiplied by 999 ohms. So that will give us 999 millivolt. Okay, so this is what your calculated value of potential difference would be. Now, if we measure the potential difference across the resistance using a perfect instrument that is devoid of all kind of error, including the error due to least count and including any scope of human error, then we should end up with this value. All right, if we are using a perfect instrument to measure this potential difference. Now, what happens when we employ a voltmeter? Let's try to understand. So in this circuit, if I use a voltmeter to measure the potential difference across R, which was like 999 ohm. Okay, so what will I do? Something is wrong. Okay, what will I do? I will connect a voltmeter like this. Okay, I will connect a voltmeter like this. Now, what impact will it have? Let's try to understand that. If I name this point as X and if I name this point as Y, then you will agree with me that if I say that the resistance across XY point is now less than 999, because this voltmeter will also have some resistance, okay, some value of resistance will be there. And because of that, these two are now, we can say that they are connected parallelly. So the equivalent value will be less than 999 as well as the resistance of the voltmeter. Okay, so overall the resistance of this setup is of this combination is less than 999. We can actually calculate it also. It will be 999 into, let's say, RV, where RV indicates the resistance of the voltmeter, divided by 999 plus RV. So this is the resistance between X and Y point, which means that I can draw an equivalent circuit like this. I can say that, okay, let there be one resistance with value of RXY, okay, and whatever is the potential difference between X and Y right now, that would be the reading of the voltmeter. So if I try to find out the potential difference, I will have to do I into RXY, and this I would be how much? It would be 1 divided by 1 plus RXY, okay, into RXY, and then uh, this RXY, I'll substitute it here, okay. I'll go to the next page. So I'll rewrite VXY as RXY divided by 1 plus RXY, or I can say that it is 1 upon 1 by RXY plus 1. Check this, and therefore it will become 1 upon RXY. So that will become 999 plus RV divided by 999 into RV plus 1. Okay, in other words, it will become 999 RV upon 999 plus RV plus 999 RV. Now, if I divide this entire thing with RV, we get 999 upon 999 by RV, okay, plus 1000. This is what we get. So from here, it is very clear that if I say RV is infinite, that is the case of an ideal voltmeter, which we do not find in practice. If I say that RV is infinite, we get the same value, the value that we got previously, that the value that we got theoretically, that is 999 millivolt. Okay, but if RV has any finite value, like if it is not infinite, then this would be a number, like something will get added to 1000. The denominator will become more than 1000, and therefore this will be definitely, it is going to be less than, okay, not much less than, it is going to be less than 999 by 1000. That means we are going to end up with a value which is different from what we were expecting from theory, although we are saying that there are no errors involved. Even the theory suggests that we will get a different value than what is. So let's try to understand. This is all mathematics, but let's try to understand in the what happened in the world of physics. So when you connected this voltmeter, you effectively reduce the resistance here. In other words, you effectively reduce the resistance of the circuit. So you increase the current. Now the current passing through the battery will be larger. Okay, so once you connect the voltmeter here, the current passing through the battery grows as compared to the previous case. And therefore, the voltage drop across this resistance becomes more. Okay, like this value, this resistance is still 1 ohm. Current has become larger. So the voltage drop here has increased. But the total voltage drop across these two needs to be 1 volt. So the voltage drop across this combination will decrease. All right, and therefore the potential difference decreased. All right, so the point here being that if we use voltmeter, then we get faulty results, because the moment we connect it, it changes the value that we were trying to measure, and then it measures the changed value. All right, getting my point? It first alters the potential difference that you were trying to measure, and then it measures the altered value correctly, and therefore we get a different value from what we were expecting. So voltmeter has got some problem. Now, how does potentiometer resolves this? Okay, so let's understand what is the idea behind a voltmeter. Okay, so sorry, idea behind potentiometer. So let's look at this idea. What is the idea behind potentiometer? Okay, what is the idea behind a potentiometer? So guys, let's think about something. Let's say this is a battery, the EMF of which is not known to me. Okay, and I want to measure this EMF accurately. Okay, now the moment I connect a voltmeter here, it starts, the circuit gets completed, the battery starts sending current in the circuit, and therefore the potential difference across the terminals, it becomes lesser than the EMF, and I get a faulty value. So using a voltmeter won't help me. Instead, what I'm planning to do, I'm planning to connect another battery here, the EMF of which is within my control. Let's say I can control the EMF of this battery. Okay, it's a magic battery. I can turn a knob and I can increase the EMF of this battery. Let's say I can do that. Let's say I've got a battery like this. This battery may have some internal resistance also. So what I do, I put a galvanometer in the circuit and I create this. Okay, now I start the value of E prime from 0 to something. I start turning the knob so that the value of this current, this EMF will rise from 0. So when it was 0, you can understand that there would be a current in the circuit, and this current would be given by E minus E prime divided by R plus R prime. And this current would be visible in the galvanometer. Like the galvanometer will show some reading, and that reading would be equal to this with some error maybe. Okay, now why error? Because there is a galvanometer, it has got some resistance. So let me put RG also here. Okay, so this galvanometer, obviously it has got some resistance, and that resistance becomes the cause of error. So I've considered that resistance also. Now pay attention guys, when E prime was 0, this value will be non-zero and we will see some reading in the galvanometer. Okay, think about this. As we keep on increasing E prime, what happens to the reading of the galvanometer? You answer this question, everyone. As we increase the EMF of this battery, okay, the current passing in this circuit, or in other words, the reading of the galvanometer, it goes down, it goes down, it goes down, and we will stop turning the knob that we are turning, the knob which is responsible for increasing the value of E prime. We will stop turning the knob the moment galvanometer starts showing us zero deflection. Okay, so I can say that when this galvanometer shows zero deflection, at that moment these two EMFs must be equal, and this statement does not depend on the value of R prime or RG. Okay, so if the galvanometer shows zero deflection, we are very sure that whatever is the value of E prime, the same value would be of E. Okay, and E prime is something that is known to me at all times. Remember, I am controlling the EMF E prime. I am controlling that by turning the knob. Okay, the knob can have numbers. It can clearly indicate me the value of E prime. The moment I see zero deflection in the galvanometer, I I become aware that these two have become equal. Whatever the value of E prime is, I can see that, and therefore I can declare the value of E, and this is without error, because at this moment when I'm declaring them to be equal, at that very moment there is no current in the circuit. So we are measuring the potential difference between these 2 points without drawing any current from the battery, and therefore whatever we are measuring is the accurate value. So this is the whole idea behind a potentiometer. Now I think that should be enough. Like if I have a magic battery like this, I'm done. Okay, but the problem here is, guys, that we do not have these magic batteries. We don't have such magic batteries that we can readily use. So what we do, we use the concept of equivalent batteries. We know that circuits can be changed to equivalent batteries, like a combination of several battery. Okay, we can replace them by a single battery, and that battery is called the equivalent battery. So I'm planning to create a circuit that can act as a battery with variable EMF. Okay, so I'm going to do that. If I'm successful in doing that, then whatever is present here, like the entire setup that is going to behave as my magic battery, that will be called the primary circuit. It is called the primary circuit of the potentiometer. So primary circuit is the one which serves as your magic battery, and the circuit or the region or the entity across which you are trying to measure the voltage, you're trying to measure the potential difference, that is called the secondary. That is called the secondary circuit. Okay, so primary circuit, secondary circuit, usually in books or while teaching, teachers tend to draw primary circuit at the top and secondary circuit at the bottom. I will do the same thing. Okay, so now the question comes that how do we make a primary circuit? Okay, so let's see. Okay, so we are focusing on primary circuit, that is my magic battery. How do I create that? Okay, so primary circuit of potentiometer. So let's do this. All right guys, so what I will do, I will start with any battery, any battery that has got any internal resistance. Let the EMF be EP, let the resistance be RP, because I know that I'm drawing the primary circuit, therefore I'm using the subscript P. Okay, then what I will do, I will connect a uniform wire. Okay, a uniform wire with some resistance here. Okay, let us call this wire as AB. Okay, let the resistance of wire AB be equal to R. Length, let us say that length is L. Okay, let's say the length is L. Okay, and it's a uniform wire. It's a uniform wire. Okay, now in this circuit, if I ask you that whether any current is flowing or not, what will you say? In this circuit, there would be some current. Let's call it as the primary current, or the current in the primary circuit. That would be EP upon R, RP actually, plus R. So this much current would be flowing. All right, so if we are clear till this part, um, now let us say what I did, I put a metal rod here. Okay, I put a metal rod here. Let's call this metal rod as AX. Okay, let's call this metal rod as AX. So if this is a metal rod, are you expecting any current to enter into this rod right now? I don't think so, because the circuit is not completed. So the current of the primary circuit continues to flow in the primary circuit. Like, this is the path on which the current is flowing. Okay, this is how the current is flowing right now. Okay, and the potential of A is same as the potential of X. Now, what I did, I put another rod here, somewhere here. Okay, let's call this rod as CX, CY, let's say, where C is the point on the wire AB and Y is the other end of the rod. This is another metallic wire. Okay, and let's say the distance between the two rods was X. Okay, now if I ask you that, what is the any current enters the rod CY, what will you say? I believe that you are going to agree with me that no current enters this rod because there is nowhere to go. Okay, and therefore VC is equals to VY. Anyways, I'm calling them as conducting rods. Okay, so AX and CY, they are conducting rods. Okay, AX, CY, they are conducting rods. Okay, now because they are conducting rods, okay, we can say that VA will be equal to VX, VC will be equal to VY. Okay, so I'll do the calculation on the next page. So we are claiming VX is equals to VA and VY is equals to VC. Now the question is there any potential difference between A and C? So between A and C, there is a flow of current, there is some resistance. So definitely we expect that there is some potential difference between A and C, A being at higher potential. So VA minus VC will be given by AP into the resistance between AC, and this resistance can be written as total resistance by length into the length X, and IP can be written as EP upon RP plus R, okay, into R by L, okay, into X. So this entire thing is the potential difference between A and C, or in other words, this is the potential difference between X and Y. Okay, so Vx minus Vy, we got it as something into X, where this something is this entire thing. We can write it as AP upon RP plus R, okay, into R by L, and this is called as potential gradient. Okay, I'm pretty sure you have heard the word gradient earlier also. If not, I'll explain it in a short while. But okay, this is called potential gradient. Okay, what's so significant about whatever we have done here? See, what we have managed to do. We have managed to find out potential difference between 2 points as a function of X. X is something which is in our control. So what I'm suggesting is that if I, pack this entire thing, when I say pack, you don't have to literally pack it. You just have to imagine it as a closed box, as a box inside which you cannot peep. Okay, so this is a box and there are two wires coming out of the box, much like the terminals of a battery, and there is potential difference between these two terminals also. So this is your battery. Now this is a battery, these are the terminals of the battery. X being at higher potential, it will be called as the positive terminal of the battery. Y being at lower terminal will be called lower potential, will be called as the negative terminal of the battery. There is potential difference, and that potential difference is controllable. Okay, why? Because it is proportional to X. So if you start sliding this rod, okay, you will notice that the potential difference between X and Y is increasing. This is something that we wanted from our magic battery. We wanted that if we turn the knob, this E prime should increase. We are not turning the knob, but we are doing something that we wanted to do. We are able to control the potential difference or the EMF of this battery. We have to slide this rod and the EMF will continue to increase, and therefore this entire setup can be used as the primary circuit of a voltmeter. All right, so so these are the points that you need to remember. Okay, now before we move further, I'll show you how to use the potentiometer, but before that, let me talk about some very important points. Okay, so what are those points? Okay, first point, let's talk about potential gradient. Okay, so potential gradient is EP upon RP plus R into R by L. If you notice carefully, potential gradient has got unit of a volt per meter. This is same as electric field. Okay, not only that, we use the word potential gradient for electric field. In fact, the electric field is actually the gradient of potential. Okay, so what is this lambda representing? This lambda is representing the electric field in this wire. Okay, the moment we close this switch, we made the circuit complete, the current starts flowing in it. When current is flowing through a conductor, or let's say when a current is flowing through a resistor, there is an electric field inside the resistor which is responsible for the motion of the free electrons. So there exists some electric field in this wire. Okay, and lambda represents the value of that electric field. So, and therefore, electric field multiplied by the distance is giving us the potential difference. That's how you calculate potential difference in a uniform electric field. You multiply the field with the distance to get the potential difference. That is what we are doing. Exactly, that is what we are doing. That we are getting the potential difference as lambda into x. So this represents electric field inside the wire. Okay, but there is a very important point to keep in mind that the primary current is flowing like this. So this value is the electric field when the current of primary stays in primary. Okay. Um, Second point. See, to understand second point, let's move to our this circuit. The idea behind voltmeter potentiometer. Suppose suppose this battery has got an EMF of 12 volt, but we don't know that because we are trying to measure the EMF of this. But this magic battery has got a limitation. The EMF in this can only be raised till 10 volt. So now I can keep turning the knob. The maximum that it will go is 10. And this unknown EMF is 12. Do you think that I will ever get a zero current in the circuit now? All right, we will not. So the limit to which this E prime can go, the limit to which this E prime can go indicates the limit of unknown EMF that you can measure. For example, the values that I took, a few moments back, if this can go up to 10 volt, then we can measure unknown EMFs up to 10 volt, not more than that. Because if this is has got any value less than 10, then we will be in a position to get the zero current. Otherwise, we are not getting the zero current. So here in this case, what is the maximum value of Vx minus Vy that we can get? Maximum value of Vx minus Vy. So Vx minus Vy is increasing when we are increasing the value of x, and x can be increased maximum to L. Okay, so Vx, the maximum value would be lambda L, which is EP by Rp plus R into R. So this is the maximum value of unknown EMF that a potentiometer can measure. And one thing you should also notice that this is less than EP. Okay, so EP serves as a rough limit of the EMF that you can measure. So whatever EMF you have used in creating the primary circuit, all right, you definitely can't measure till this EMF also. All right, but it can serve as a rough estimate of the limit. For example, if I'm using a 2-volt battery in creating a primary circuit, then in no way I'll be able to measure 2 volt from this potentiometer. Okay, unless I have an ideal battery. Okay, because if we have an ideal battery, then things change. In an ideal battery, Rp would be 0, and then this will become EP. Okay, so EP serves as a rough estimate of the EMF that we can measure. Okay, so one point is this, second point is this, keep this in mind. The third point that you need to keep in mind is that, again, let's go to the idea here. Guys, what would have happened if I reverse the polarity and if I try to measure the unknown EMF? Okay, if I reverse this polarity, the two EMFs get added up. Okay, the two EMFs get added up, and now we will not get a zero current at all. Okay, so we have to ensure that the primary battery and the secondary battery, they oppose each other during the measurement time. In other words, we know that potential is decreasing as we are moving from A to B. So when you're trying to measure the unknown EMF, the higher potential should be towards left, or it should be towards A, and the lower potential should be towards B, so that it can happen. So we have to keep in mind that polarity, okay, needs to be polarity needs to be proper for measurement. Okay, what proper is, the proper thing is to keep the higher terminal or higher, you don't know the EMF of the unknown battery, but you know that which is the positive terminal, so that should be towards A and the other should be towards B. Okay, now if you are clear with these 3 points, let us talk about how to use potentiometer to measure EMF of unknown battery, unknown EMF of a battery. So use of potentiometer. Okay, so the first use of a potentiometer is to measure EMF. Okay, guys, there's one more thing it might have come to your mind, or you might be thinking that how do we know all these numbers? Like if I'm creating a circuit in a battery, a primary circuit in the battery, then I need to have a battery with a known EMF, with a known internal resistance. I need to have a wire with a known resistance, with a known length. That is too much to ask, which actually is too much to ask. So we actually don't measure lambda. We never measure lambda. Rather, we calibrate it. What does that mean now? Let me show you. So let's say I prepared a primary circuit. I don't know the resistance of this wire, I don't know the length of this wire, I don't know the internal resistance, I don't know the EMF. I know nothing. I know nothing. Okay. What I will do, I will take one battery, the EMF of which is known to me. Okay. Let's call it as E1. Okay, with internal resistance R1. And this is a switch, let's say S1. And then there would be the other battery, the EMF of which I'm trying to measure. Let's call it as E2. Okay. So E2 is what we are trying to measure. Okay. Let the internal resistance be, and then I'll connect a galvanometer here, and then I'll connect it here. So these 2 points are serving as points X and Y. Wait, so let's say this point is your X point and this point is your Y point. This is jockey. We plan to slide the jockey. Okay. And let this length be L. Okay. So the distance between the 2 points is L. Okay. Now what we will do, we will first close S1 only. We will first close S1 only, and we will start sliding the jockey from left hand towards right. Okay. And let's say at L equal to L1, okay, galvanometer shows zero deflection. Okay, right now only S1 was closed, S2 was open. Because S2 was open, okay, so the lower battery was irrelevant. Okay, so this was the battery that we corrected, and we are trying to measure EMF of this. Okay, so we will write E1 is equals to lambda L1. Okay, and remember that E1 is known to us. L1 we have measured. From here we can get the value of lambda. We don't need to calculate it. We will measure it experimentally, and then we will open switch S1. We will close switch S2. Okay, and then we will again do the repeat the experiment. If we get null point, you know, the value, the place of the jockey, the location of the jockey where you get zero deflection in the galvanometer is called a null point. Okay, so at L equal to L1, let's say the galvanometer again shows us zero deflection. In that case, the equation that would be applicable now, okay, now E1 is out of the circuit, so E2 will become equal to lambda L2. And then what we can do, we can divide these two equations to get rid of lambda, and we will easily get. So E2 by E1 will be equal to L2 by L1. And from here, you can calculate the value of uh, E2. Getting it? So this is how we can measure the unknown EMF of a battery. So this is one way. Okay. If I give you some numbers, okay, like for example, when E1 was 30 volt, L1 was, let's say, 40 centimeter, and when L2 became 60 centimeter, we got the null point. So what is the value of E2? Okay, you can easily find the answer. E2 would be E2 would be, what did we write here? L2 60 by 40 into 30. So how much is this? This is 3, this is 215, 45 volt. Okay, this is 45 volt. Now, in the same situation, let me just modify and ask you a question. Suppose R1 is given to be 6 and R2 is given to be 3. Okay, let's write it here. Okay. In the previous question, R1 is 6 ohm, R2 is, let's say, 3 ohm. And then we have closed S1 and S2 together. Okay, we kept S1 and S2 close together. Can you tell me the location of null point, where the null point will come? Try this question out, everyone. I'll tell you, like, you can pause the video and you can try. So we will first calculate equivalent EMF. You understand here? If we keep both S1 and S2 closed, this entire setup becomes like a parallel combination of the battery, and the equivalent EMF will be given by what? It would be E1 by R1 plus E2 by R2 upon 1 upon R1 plus 1 upon R2. So it will become, E1 was 30, 30 by 6 is 5. Okay, then 45 by 3 is 15 divided by 1 by 3 or 1 by 6 plus. So this becomes how much? This is 20, and then 9 into 18. So this becomes 40 volt. Because you have equivalent EMF, you will next write that E equivalent is equals to lambda into L3. So L3 is what we were trying to find out. It's 40 by lambda, and lambda can be substituted from equation number 1. Equation number 1, E1 by L1. Okay, so E1 was how much? E1 was 30 and L1 was 40. So the answer would be 160 by 3 centimeters. So all right, so this is how we can measure, like we not only measure the unknown EMF of the battery. I extended the question to, to explain further. Now let's go to the second usage. Okay, let's go to the second usage, which is measuring internal resistance of a battery. Okay, so again, things remain the same. We will create a primary circuit. We need not know the EMF and the resistance of the primary circuit. Okay, and then there is a battery, internal resistance is there, we will connect another resistance R naught. The value of R naught would be known to us. Okay, the value of R naught would be known to us, and this is the galvanometer. Rather, I will place the switch at a different location. Okay, the switch will be kept here. This is your galvanometer and this is your jockey. So again, this point, let's say, is X, this point is Y. Okay, so when the switch is open, okay, let's say this EMF is E and this is R, we are trying to measure R. R naught is known resistance, we know it. Okay, R naught is known resistance. Okay, R naught is known resistance. So when the switch is open, this resistance is useless, this EMF is getting balanced. So let's say initially the length is L1. Okay, so we will write E is equals to lambda L1. And then when we close this switch, what happens is, this is important, everyone please pay attention. When we close the switch and then we keep on sliding the jockey until we get a zero deflection in the galvanometer, understand this, if there is zero deflection in the galvanometer, there cannot be any current in this branch. Okay, if there is no current in this branch, then the situation is like we have two independent circuits. This is a single loop circuit, this is a single loop circuit, and we have connected the two single loop circuit via a wire. Okay, a single wire. So when you connect two different circuits with a single wire, do you think some current will flow in this wire? Do you think that if we put some combination of battery and resistance here, some combination of battery and resistance here, do you think that there can be a flow of current in this wire? Two independent circuits connected by a single wire. Do you think there can be a current flow in that? The answer is no, because if it is there, there cannot be any sustained current. If a current exists there, then node rule will get violated at this node. You can check that the incoming current is I. Okay. Now, if the outgoing current is I1, the same I1 current will come from here. Okay, so the node rule doesn't satisfy. Okay, it becomes I plus I1 is equals to I1. So I has to become 0. Okay, I has to become 0. There is another logic to explain that there cannot be any current. Okay, suppose I divide the universe into two parts, the left part and the right part. What I'm saying is that if there is a current in this wire, it is continuously draining the charge from left part and it is providing charge to the right part. It is draining positive charge from this and it is depositing there. So this way we cannot get sustained currents. Okay, this is not, we cannot get sustained current. So two independent circuits connected by a single wire, we will not expect any current to flow in that wire. So the same situation is happening here. Okay, the same situation is happening here. If there is a zero current in the galvanometer, there cannot be any current in this branch. That means these two circuits are now independent, and therefore the current of primary stays in primary and the current of secondary will stay in the secondary. This is the primary current and this is the secondary current. Okay, if you slide jockey to any other position, then galvanometer will show a non-zero deflection indicating that there is some current here, and therefore there should be some current here also. All right, which means that when galvanometer is not showing any deflection, the entire thing can be looked upon as two independent circuits which are single loop, two single loop independent circuits. But when galvanometer is showing any reading, at that time we have one circuit instead of two. We have one circuit which is a three loop circuit. Are you getting it, everyone? When the galvanometer is showing zero deflection, there would be no current here, and therefore we have two circuits which are single loop in nature. When the galvanometer is showing deflection, we have one circuit which is a three loop circuit. So keep that in mind. Now, if the galvanometer is showing zero deflection, we will say that whatever is the potential difference across these two, the same is the potential difference across these two. And the potential difference across these two can be calculated from the lower branch. We are going to write I secondary into R naught is equals to lambda into L2, and I secondary will be written as E by R naught plus R into R naught is equals to lambda L2. So if you divide 1 and 2 equation, okay, when we do that, E gets cancelled, lambda gets cancelled, and we get R naught plus R by R naught. Okay, R naught plus R by R naught is equals to L1 by L2. In this equation, only R is unknown. We know the value of R naught, that's our known resistance that we put. Okay, and L1 and L2 is measured. So like this, we can find out the internal resistance of a battery also. Okay, now to highlight the point that I was indicating here, that it would be a three loop circuit, let me give you a question, guys. Okay, it's a very good question, fabulous question. Okay, so let me do that question with you. Okay, so here, the potentiometer wire AB is 600 meter long. So this wire 600 centimeter long. Okay, 6 meter wire. At what distance from A should the jockey J touch the wire to get zero deflection? So in the situation shown, let's see what, so the values have been given to us so that we can calculate the value of lambda. So right now I will calculate lambda as, notice it is E divided by R plus 15R, that is 16R, into 15R by 600. Okay, so this R gets cancelled. Okay, so this is 15E by 16 into 600. Of course, I can cancel it out. I'm not doing it. Okay, let's do it. So this will become 40. So it will become E divided by 64. So this is the value of lambda. Okay, now when the galvanometer shows zero deflection, E by 2 is the EMF that gets balanced. So we will say E by 2 is equals to lambda into, the question is asking us for the balance length. So let it be L. So lambda is E by 640 into L. So from here we get L as how much? This L gets cancelled. I guess we get 320 centimeters. So this is the distance of null point from the end A. Okay, now the question says if the jockey touches the wire at a distance of 560. Now notice that we are getting null point at 320. So if we touch the jockey at any other point apart from 320, the galvanometer will show non-zero deflection, which means that it is there will be current in this circuit. Okay, what will be the current through the galvanometer? We want to know the galvanometer reading. So in this case, let's understand. So the entire length is 500, 600, and the resistance is 15R. So what is the resistance? Resistance of length 560. 560 was the value. Yeah. So resistance of length 560, that would be 15R. Okay, 15R divided by 600 into 560. So that is this is what, 14. So that is 14R. Okay, so the equivalent circuit that we will draw is this. There is a battery, there is a resistance, this is E. Then we have a resistance of 14R here. We have a resistance of R here. Okay, and then there is another battery of EMF E by 2 with a resistance, some resistance was also there with a resistance R. Okay, and this is connected. So this is your equivalent circuit, and here is where the galvanometer is connected. We want to know the current in this branch, or we want to know the current in the low. So it's a two-loop circuit now. What remains to be done is that you have to solve this two-loop circuit. Okay, let me do it for you. Of course, you all can do that on your own. So this R and this R, they are connected in series. So we have E with 2R. Okay, E with 2R. Then we have a 14R here. Okay, then we have a 14R here, and we have an E by 2 here. Okay, and R here. Okay, so this is my equivalent circuit. Okay, how to solve this? You can solve by point potential method. You can write equation. I'm not finishing this question, guys. Actually, I thought I'll finish it, but I can do that. We want to know the current here now. Okay, so let's treat this as a equivalent battery. Let's treat this entire thing as equivalent battery. So I'll assume a 0-volt battery here, and these two are connected parallelly. So the equivalent EMF would be E by 2 plus 0 by 14, okay, R, divided by 1 by 2R plus 1 by 14R. Okay, yeah, so how much will that be? Let me do it here. It was E by 2 upon E by 2R upon 1 by 2R plus 1 by 14R. So it becomes E upon 2R, and then 14 plus 2 is 16R into 14 into 2R. 2R gets cancelled. So this is that would be R square. So we get 7E by 8. Okay, 7E by 8 is the, and then R equivalent would be 14 and 2. Okay, this is to R. Okay, 14 and 2. So 14 into 2 upon 16R. So this becomes 7 by 4 ohm R. Okay, I hope I'm doing it right. Yeah. Okay, so that's it. Now we have one equivalent battery, one equivalent resistance, and they are connected with this branch, which is E by 2 and R. Okay, so the current would be 7E by 8 minus E by 2. Okay, so 7E by 8 minus E by 2 divided by total resistance, so R equivalent plus R. So that will become 7 plus 4, 11R. 11R by 4. So this becomes what? 4. 7 minus 4, 3. 3e by 8 into 11r into 4. So 3e by 22r. That would be the right answer. All right, students. So that is how we solve questions related to potentiometer. I hope you understood the entire concept, guys. The more you practice, the better you will become at this topic. I hope you enjoy this and keep watching this series, guys. I'm going to bring those concepts to you in this series, which are usually not understood by the student in the regular classes or which are not taught in the regular classes, but they are relevant from the perspective of JEE Advanced. So that is the purpose of this series. Take care, everyone, and I'll see you in the next session. Bye bye.